Good afternoon, everyone. I am Shreyank, and I will be presenting my paper StegColNet, Steganalysis based on an ensemble color space approach. As part of this presentation, we will briefly look at introduction, related work, Steganalysis approaches, followed by the building block of this work, ColorNet, our approach overview, architecture of the proposed approach, results, and conclusion. Steganography is a means of covert communication in which secret information is embedded into some form of digital media, such as an image, video, or text file. Usually, this form of embedding is done such that there is no apparent perceptible change in the embedding file. There are three main properties that a steganographic algorithm should possess: security, robustness, and capacity. In case of an image steganographic algorithm, security would mean how securely the algorithm can hide information. That is, how little visual change is caused in an image using an image steganography algorithm. Robustness refers to the invariability of the steganographic algorithm when an image is subject to different transformations such as scaling, resizing, rotation, etc. The capacity, on the other hand, represents the amount of data that can be embedded in an image before there is a noticeable visual change in the image. Steganalysis is the process of detecting if a given image has information hidden in it or not. In this regard, we can convert this problem into that of a simple classification problem. To detect if an image is embedded with information, we propose to use an ensemble color space model. Recently, it was seen that an ensemble color space model, the ColorNet, obtained excellent results on large-scale image classification datasets such as ImageNet. Based on this, we propose a novel steganalysis approach. Steganalysis is the method of trying to either determine a stego image where information is hidden, or extract the secret information. Our method deals with the former. We treat the problem at hand to be a classification problem, wherein each image either contains some hidden information or not. There are two basic approaches to steganalysis: signature steganalysis and statistical steganalysis. Signature steganalysis is the method wherein patterns or signatures relevant to various steganographic algorithms are searched for. The presence of a pattern indicating the secret information is being hidden in the image. The quintessential process here is the repetition of patterns due to embedded secret information. The statistical approach researches for mathematical results to determine if the information is being hidden. Signature steganalysis is further classified into specific embedding and universal blind steganalysis. Specific embedding approaches are impractical because we need to know what steganography approach has been used to embed information. Hence, universal blind steganalysis is preferred. These approaches help in the extraction of high-dimensional features. To reduce the feature size, common algorithms such as wrappers and filters are used. Filters are less complex, but they perform poorly. Wrappers, however, are more complex and time-consuming. To overcome this, meta-heuristic approaches have been deployed. These approaches solve optimization problems by utilizing natural phenomena. It was seen that gray-wolf optimization performed better than meta-heuristic approaches for solving nonlinear problems in a multidimensional space. However, it has a slow convergence rate and gets trapped in local optima at times. It has been seen that the gray-wolf optimization can be optimized by modifying its parameter A to obtain a quick convergence rate, better convergence precision, and higher agility for global searching. As part of our prior work, ColorNet, which was published in the Asian Conference on Computer Vision 2018, we showed that certain classes of images are better represented in certain color spaces. We showed that combining the outputs for each color space will give us a much higher accuracy in comparison to individually using each color space. We also showed that a relatively small model can obtain a similar level of accuracy to recent state-of-the-art approaches. For example, if we see in the paper, the experimental section shows our model with 1.75 million parameters can provide a similar accuracy to that of a DenseNet model with 25.6 million parameters for the CIFAR datasets. Recently, the effect of color spaces on image classification has been explored. It was seen that individual color spaces inherited classification features explicitly to themselves. This helped us ponder about the ability to extract information in an image where there is secret information being embedded. ColorNet, being an ensemble model that could extract features specific to each color space, was an excellent choice to utilize to help us in determining if an image could have information hidden in it. The output of ColorNet is a high-dimensional vector which causes a computationally intensive execution. To reduce the number of features selected, we have to use an optimization approach for feature selection. We used weighted averaging to obtain a single feature map from all the individual feature maps that are generated by each color space. It was seen in ColorNet that each color space had features explicit to themselves, and this would help us detect minute changes in the image. We then use a levy-flight gray wolf optimization method, which is a meta-heuristic approach, to select a smaller subset of features. Using these features, we classify the given image into one of two classes, containing concealed information or not. The reason for selection of the levy-flight gray wolf optimization is based on the statistical results obtained in the reference number 14. It was seen that for 15 defined benchmark functions, the Wilcoxon rank sum test of Levi-Flight gray wolf optimization outperforms existing optimization approaches in terms of mean fitness values. For further technical analysis, please refer to the paper. So the architecture of the approach is listed here, where we can see at training stage, a sample image is taken of concatenated feature map using the aggregated heat map is obtained, and using Levi flight, we can obtain features. So at the stage of testing, when an input image is given, again we generate the aggregated heat map, and then we perform a simple classification as to whether the image is hiding information in it or not. Most commonly used Steganalysis datasets are the Bossbase and BOWS2. Each contains 10,000 grayscale images. However, the approach proposed is dependent on color, and as such, we use a dataset with color images. Hence, starting with the 10,000 images of Bossbase, we generate a dataset by following the process done in reference number 4. We downsampled the full resolution images to a size of 512 cross 512. We then followed the process in reference 4, wherein uh, the training and testing scenarios would be conducted in a similar environment. Two datasets were created by using two democycling algorithms, pattern pixel grouping, and adaptive homogeneity direction. And these were named BOSS PPG LAN and BOSS AHD LAN correspondingly. Further, by removing the downsampling method, we can obtain two more datasets, BOSS PPG CRP and BOSS AHD CRP. By pairing a democycling algorithm with bilinear or bicubic kernels, we obtain four more datasets, BOSS PPG BIL, BOSS AHD BIL, BOSS AHD BIL, and BOSS AHD BIC. The embedding payload was set to 0.2 BPC, that stands for bits per channel, and 0.4 BPC. In order to select the most challenging scenarios and also follow similar conditions for result comparison, we followed the process executed in VisorNet. To compare our results, we considered three deep learning approaches for color steganalizers. They are widely considered state-of-the-art approaches. These are VisorNet, deep hierarchical representations, and deep CNN, which are shown in the table as WNet, DHR, and DCNN. Experiments were conducted on the same datasets and using similar resources for a fair comparison. Popular steganography methods such as SUNIWARD, MEPOD, and Hill adopt an additive embedding distortion approach for minimizing framework. Recently, CMDC was proposed by improvising the CMD approach for color images. We denote the CMDC method using SUNIWARD and Hill as CMDC SUNIWARD and CMDC Hill respectively. Although DHR and DCNN can be executed in channel-wise convolution, normal convolution, and input concatenation, we show results only for the normal convolution as VisorNet outperforms DHR and DCNN in all cases. We also compare results with channel gradient correlation. As can be seen from the table, the proposed method outperforms other state-of-the-art methods for all but one case, And also the percentage increase in detection is significant when pattern pixel grouping is performed in the datasets. Further experimental analysis is done by mixing datasets. Uh, the first table here shows how the datasets were mixed. We further label the datasets in Roman numerals for simplicity to display the comparison of Steganalysis. BPL, BPBC, BPBI, BABC, BABI, BAL are abbreviations of Boss PPGLAN, Boss PPGBIC, Boss PPGBIL, Boss AHDBIC, Boss AHDBIL, and Boss AHDLAN. Similar to previous tables, this compares results on the above mentioned mixture of datasets with 0.2 BPC. As can be seen, the proposed method outperforms recent state-of-the-art approaches by a significant margin. With recent developments of color-based steganography algorithms, the need for a powerful steganalizer is needed. We saw recently that an ensemble method of color spaces has a significant impact on classification results. We proposed StegColNet as a powerful color image steganalizer. We employ an ensemble color space strategy to determine if an image is protecting information or not. We use ColorNet and take the final activation map from each color space. We use weighted averaging to obtain a single feature map from all the feature maps that are generated by each color space. We then use a levy-flight gray wolf optimization method to select a smaller subset of features. Using these features, we classify the given image into one of two classes, containing concealed information or not.